All right, so continuing on, I don't know why I stopped the video. I wasn't done, but anyways, we keep going. We're still on 17.5, and we're still looking at factors like affecting solubility. So this right here, it was the common ion effect. And next, we're gonna look at pH. So pH, this is gonna be a relatively easy one because it's mostly conceptual. There's not gonna be much math. So we have the question that asks, which substance is more soluble in acidic solution than in basic? So for A, we're gonna have nickel hydroxide. For B, we're gonna have calcium carbonate. All of these are solids, by the way. C, we're gonna have barium fluoride. And D, we're gonna have silver chloride. So let's think about this for a second. It's asking an acidic solution. So if we look at all of these in the respectable ions, we have nickel plus 2 hydroxides. We have calcium and carbonate. We have barium and fluoride. And we have silver and chloride. Okay, so if we look at all of these have a minus charge. The anions, I mean. So this comes down to knowing our acid and bases. So if it's OH, it's going to be basic. If it ends in carbonate, fluoride, any of the halogens, which are going to be on group 7, all the halogens are right here. These are going to be acidic. That's how we know these. Acidic. And this one, well, carbonate is one of those common ions that we have to know. And we know that carbonate is acidic. Okay, so what we learned from the common ion effect is that if there's a common ion, the solubility is gonna be much lower than it originally would have been. So what we can tell from this is that if we have a compound with similar properties to the solution that we're adding in, it's not going to dissolve very much, because when you're adding this to an acid solution, it's not going to be able to create many protons. It's not going to be able to produce many protons or hydrogen ions because it's already carrying its own hydrogen ions. So it's just going to produce more water, making the solution more basic. So it's going to kind of like go backwards. If it's basic, however, and we add it to an acidic solution, it's going to, these hydroxides are going to cancel out with the hydrogen ions that we're adding it to from the acidic solution, and it's just gonna make water, but we're gonna have free nickel ions floating around. So it's gonna be able to dissolve more. So at the end, this is the answer. And it's simply because nickel hydroxide is really basic with its hydroxide ions. And we know that the hydroxide reacts with the hydrogen ions to form water, leaving behind nickel ions. So that's how we know which substance is going to be more soluble, just based off of their chemical formulas and their properties. Sorry my video cut out. If you were able to notice that, is my alarm just barely turned on. Okay, the next section that we're going to be looking at is we're going to be looking at the formation of complex ions. And for this, I'm not gonna say it's relatively easy, but conceptually it's nothing new. So formation of complex ions. So for this problem, it's gonna ask us to calculate the concentration of silver ions in a solution at equilibrium when ammonia is added to a 0.010 molar solution of silver nitrate. And also it is given to us that the concentration of the ammonia, not the nitrate, is equal to 0.20 molars. So it's going to be a lot more concentrated than the solution of silver nitrate. So now, it also gives us a slight tip to neglect the small change in volume. So now, what we can do is, well, what we need to do first is we need to write what exactly is going on here. So it's telling us that we're going to add ammonia to a solution of silver nitrate. So we're going to have some silver nitrate solution plus our ammonia. And what do you think is going to happen? Well, we know that the silver is going to dissolve into its ions, so is the nitrate. And the ammonia, well, it's already its own compound, so it will just be the same. So what would happen? What's going to happen is that this is going to be left as a free ion. This is essentially going to be a single replacement reaction where the ammonia is going to replace the nitrate. And at the end, did I write this right? Silver has a +1 charge. Yeah, okay. Silver ammonia, that is what is going to be formed. And there's going to be two ammonias here because this is going to be positively charged. And again, this disassociates into its silver ions and its ammonia ions. So now, also I should probably say that all of these are aqueous. We put this in water. Well, no, not in water. We put it to themselves, but it's going to be aqueous because it's going to be a solution. And this right here, I don't think it precipitates. I think it's just going to be aqueous as well. Okay. So now we can make our ice table. So initially, there is a slight concentration in ammonia and in silver, but the ammonia isn't being added yet. So initially, we have a 0.010 solution, 10 molar solution of silver nitrate. So that's the concentration of this silver right here. Initially, we have 0, and well, this is going to be negligible because we already know the concentration of ammonia, and that's 0.20 molars. So that's going to be the same throughout the entire process, including equilibrium. So the only thing that's going to change are the concentrations of the silver, ammonia, and the silver ion. So this right here is losing its concentration. The silver ion is gaining concentration. And at the end of the day, we have our equations 0.010 molar minus x, and we have just x. So now we can write our equation for KSP, and that is just equal to the products over the reactants. And that's going to be, this should be balanced. There's a 2 right here. So there should be a 2 here. Because we have 2 ammonia ions on this side, on the other side we should also have 2 ammonia ions. And the silver doesn't change. My apologies for that. And it's going to be the products, the concentration of silver times the concentration of ammonia. And this is going to be to the power of 2 because of its coefficient. And that's going to be divided by the concentration of silver ammonia. Perfect. Now we can plug in our values that we got at equilibrium. So KSP is going to be equal to the concentration of ammonia. This is negligible, so we can take this off. So that's going to be 0.010 molars multiplied by x squared divided by oh no, I'm doing this wrong. I was looking at the wrong side. I'm looking at this portion first. These are the products, not the other side. We have x, and then we have 0.20 molars. And then on the bottom, we have 0.010 molars. So now these two, they're going to divide out. So the KSP, which was given to us, yeah, I think it was given to us. Yeah, the KSP is equal to 5.9 times 10 to the negative 8. And now we can solve for x. So we have 5.9 times 10 to the negative 8, which is equal to x times 0.2 over 0.01. So now we can do a little bit of cross multiplication. We have 5.9 times 10 to the negative 8 multiplied by 0.01 and divided by 0.2. So at the end, that doesn't look right. I don't like this. Oh right, this is gonna be squared. I don't know why I didn't square it. I'm just messing up here and there, right? My alarm cut off the video again. But anyways, what I was saying is the formation of complex ions. We're still right here in this problem. And so we have our KSP value, which was given to us, 5.9 times 10 to the negative 8, and we have our formula. So we do a little bit of cross multiplication. We get that x times 0.2 squared is going to be equal to 5.9 times 10 to the negative 10. We divide this out. X is going to be equal to 1.47 times 10 to the negative 8. So x is just equal to 1.5 times 10 to the negative 8. And that will be in molars, of course. And this is, of course, for the concentration of silver ions. So as we can see, something that we can infer is that the formation of the ammonia, the silver ammonia, and it's a complex, it's going to be a complex ion. It's going to reduce the concentration of free silver ions in our solution. and that is the formation of complex ions. So I hope you found this video helpful. If you have any questions, I'll be more than glad to answer them. Today, what is today? Today is October 10. So today, as of October 10, I will be in school earlier than lecture. I will be helping out one of my fellow peers with this kind of stuff, with the entirety of chapter 17 and some chapter 16 stuff. So if you guys would like to pass by, I'll be there in campus North Las Vegas around 2 p.m. Just sometime a little bit earlier. I don't have the times, but if you're interested, I'll be more than glad to let you know of the times. And yeah, that will be all for this chapter, as at least this is what's going to be on the quiz for today. So this is all we need to worry about. Yeah, so 17 first we covered. You can exit out of the video, by the way. I'm just letting you guys know the brief things that we looked at in this chapter. There's not gonna be like another exercise or anything, so you won't miss out. So yeah, so first we looked at the common ion effect by itself, into what it is, what it does. Next we looked at buffers. Next we looked at titrations. And then 17.4 is the molar solubility, what we just looked into. And 17.5 is the factors that affect that solubility, which is a deeper look into the common ion effect, pH, and the formation of complex ions. So yeah, that will be all for this video. I hope you found this helpful, and let me know if you have any questions. See ya.